Alright, we're looking at loan repayment, which is the second solver problem from the USACO 2020 January contest. So what's going on here? Farmer John owns Bessie N gallons of milk, where N is up to 1 trillion. It's a lot of milk. So give the money within K days, and he must give at least M gallons a day, also up to 1 trillion. Okay. Pick X, compute how much is left, divided by X. Okay. Determine the largest X. Well, this is basically exactly a binary search problem, right? I see. After K days. Okay, K is also up to 10 to the 12th. So we can't just simulate this, but I'm pretty sure we basically can. NKM. Alright, well, let's give it a try. Okay, well, so what is a maximum value for X? Obviously it has to be at least 1. Probably 10 to the 12 is fine. Yeah. Okay. We want the largest X. So if that's okay, largest X, otherwise I is X minus 1. Okay, so we need to figure out so base case here so we don't get stuck in an infinite loop. So suppose that low is 0 and high is 1, then X is going to be 0. So then we can get stuck here. So we want X to be 1 in that case. And then we'll terminate on that iteration of the loop. Okay, so how do we write OK? Okay, so this is the naive implementation, but it's too slow because we can't afford to do n iterations of a loop. After K days, not after N days. Sorry. K days. How do we speed that up? Not sure yet. Let's just try on the sample, which our solution is simply fast enough. And that's 0. That all includes sort of fine. Yeah, so we do need to speed this up still, though. Well, so if m times k is greater than n, then the answer is infinity. That seems somewhat problematic. I see. Okay, that's why they guarantee that it's less. Well, as soon as this is done, we can actually stop, because it's always going to be less than m in subsequent iterations, and actually less than or equal to is all we need. Does that happen fast enough? It's very hard to say. Probably. I don't know. So suppose n is 10 to the 12. Actually, you don't have to suppose. You can just do it. nkm. And k should be 6 over 2. And m should be 1. Yeah, okay, so we should step these steps forward too. So how many distinct values can y have? So y changes when n minus g changes by x. Right, the point is that like like this. So we can do many iterations at a time. be? So we're doing many iterations of this loop at once. The idea here and these are designed to leave it so that y will be the same on all these iterations, and then this one might change it. And we need this one because amount might be 0 if we're very close to a change. How does the speed up work? Okay, so if we get down, okay, so this is how many days it's been, this is how much we've given. So, you know, well, the number of days is less than k. Compute how much you're going to give on this next day. If it's less than or equal to m, then you're done. You know you're always going to give m on all the subsequent days, so just fast forward time through that. Right, so just this is how many days are left, give m on each of those days, set t equals k. We're done. This way of thinking about it is a little clearer. So if we're not done, then we want to fast forward through a bunch of iterations of this loop. So y changes. So the point is that y only changes when you cross a multiple, when n minus g crosses a multiple of x. So how much further down do we need to go until we cross a multiple of x? That's exactly n minus g mod x. So that's what we're going to fast forward through. And just to check that we did the math right, we're going to assert that n minus, right, so if we, so what we're saying is we can add this, we can keep giving this much and y won't change. So let's assert that n minus g plus till change divided by x is still y. And then we can do the fast forwarding. So how many days of that are there going to be? Well, there's just going to be how much, you know, we can give divided by y, because we're giving y per day. So do that fast forwarding, right? Just give amount days of that. So n days, make it clearer. Do n days of that. And then, you know, on the last day, it's also going to be y. So do that, you know, give y on that day. And now we should be at a new value of y. Maybe we can even assert that n minus g divided by x is not y. Right, this is asserting that we didn't fast forward too far, and this is asserting that we fast forwarded far enough. And by the way, we definitely do need to do this because this can be 0 if till change is less than y. Cool. And that also passes, so we fast forwarded exactly the right amount. Nice to see with the asserts. And then it's just a binary search, which is really, I think, somewhat clear from the problem, right? It says, give me the largest x, such that if you do something, you know, such that some Boolean function is true. This is like literally the thing that binary search is for. so finding the largest number such that some Boolean function of that number is true. Assuming that it's monotone, so that it sort of strictly switches from true to false at one point. Right? That is that if we pick too large a value of x, we won't pay off the loan. And so to actually see the binary search would work, we should show that basically the bigger the x that you pick, the smaller the total amount of milk that you give. This is actually pretty clear every day. If x is bigger, this number is smaller. And then if g is smaller from the past, actually g is smaller from the past, then we're going to give more today, which is pointing in the wrong direction. Okay, so it's not actually totally clear to me that this is true, that the bigger the x always, increasing x can only cause you to fail. I don't know, it seems extremely, I believe that it is true, I'm just not sure how to show it. Yeah, I guess maybe the argument is that you would always rather have already given a gallon in the past, even though that might make you give less today. It's only going to make you give at most one less. So x is positive. And so the total amount that you'll give will be higher if you gave more in the past. So that combined with the fact that increasing x always decreases the amount that or decreases or leaves the same the amount that you could give today. Okay, I think that's actually convincing. Yeah, so binary search, we can do a standard binary search. So pick some bounds. I had to think a little bit about if 1e12 was big enough. But it should be, because 1e12 means that we're only giving 1 gallon a day, which is not enough to pay off the loan. Okay, so now that we've picked our bounds, you can just keep cutting until the lower and the upper bound match, and then that must be the answer. And so this requires a little bit of care. Right? Notice the +1 here. Sometimes it's +1, sometimes it's +0 or nothing. So how do you tell? Right, so first you should write this part. So if this x was good enough to pay off the loan, well, we want the highest value of x that pays off the loan. So we know that this value of x works, so the answer must be greater than or equal to this. So low, right? These are supposed to be an inclusive interval. So the loop invariant, right, inclusive on both ends. So if this answer works, then the answer must be greater than or equal to. If this answer doesn't work, the answer must be strictly less, because we need a value of x that does work. So we get this x minus 1. And now we can decide if it's +1 or +0. So always consider the case when low is 0 and high is 1. If we don't have the +1, then that gives us that x equals 0. And so then our next iteration of the loop could go back to 0, 1, right, if it's this case. Or it would go to 0, -1. So that seems wrong. So in the case where low is 0 and high is 1, we actually want to test x equals 1. So that's why we do this. Pretty much every time I write binary search, I try to think through whether this is +1 or +0 in this way. And that's nice because it saves you from having to do some kind of sloppy. Another way to do binary search is don't think about that, and just well, they're far away, and then you can do a little for loop over from low to high at the end. But it's nicer just to get it right from the start, and it's not that hard. So anyway, we do a binary search, we find the highest value of x that returns OK here, and then we just print it out. So that's the problem. So let's see if we get the right answer. I need to do the FE open stuff. FE open. Own dot in, read sped in, out, write sped out, and cool. Loan.cc. Okay. Let's see how we did. Looks good.